Hello, everyone. This is the second episode of Warehouse Modeling using FCalc from ArcCalc. If you would like to watch the first video, navigate in the sidebar to ArcCalc Learning Center. You'll find the first video, and this video will be uploaded here. In the previous episode, we've modeled the main structural elements, the geometry, dividing the frames, applying supports, and we've ran um, sanity check, just one analysis to see if the moments, shears, and reactions are making sense. In this episode, we'll be applying or assigning the section to all of the frame elements, applying the loads, gravity and wind loads, and reading the results. We will also verify the results. So on um, that was the structure that we have modeled together, and the sections assigned to be assigned to the frames are 460 UB, 67 kilos from the Australian library catalog. That is spanning 28 meters between the support, which is the stanchion in the middle, in the mid span here, to that or onto the transfer beam at the valley there between the two warehouses. Stanchions are 310 UCs, 118. So we will apply those section assignments, and then we'll be talking about the loading. Section assignment will be as easy as looking at the 3D view as it shows there. So we'll select, first of all of the columns in one hit, and then all of the columns are selected. Click on the section assignment, and then if you are using Australian standard or American, European, British, or Chinese library, just pick the appropriate library. In this example, we'll be doing the Australian. So 460 UB is there. Sorry, 310 UC. So we just navigate to UC and go to 118 and then assign. So all of the sections have been now assigned to the columns. And then now we'll navigate to the beams. So all of the beams and the rafters are 460 UBs, whereas those longitudinal elements will be just 100 PFC being spanning at 6 meters only. These will be receiving the purlins. Now we'll just go on the 2D view. So frame-wise, we can do it frame-wise. For example, go in there, select, hold on control, select all of those elements on the elevation, and then go to UB 460 and assign. So we missed this one, so assign. So the sections have been assigned. Now everything with F without a section assignment will be just like default section, which is the concrete section, 600 by 600. You can also assign the sections by selecting those on the 3D view as well and assigning. I'll carry on with assigning all of the sections. I'll speed up the screen to save some time. Now all of the sections have been assigned. If you want to preview the sections, just to make sure everything is making sense, just go to Options menu, where you can look at nodes, labels, local axes, or extrusion. This is what I'm after at the moment, extrusion. Once it's turned on, you'll see the difference between the section sizes for the rafters, the 100 PFCs and similar. You can spin around, and while assigning sections, I'd recommend that you turn on the extrusion just to make sure you're on top of all of the frame elements without missing anyone. Next is applying the loads. Um, I'll be sharing this calculation summary later. But we've got in dead loads, live loads, and wind loads. Dead load can be estimated if we are using color bond, probably 5 kilograms per square meter would be appropriate. The on weight of the steel beams, you can do it by liquidating the kilogram per linear meter over the tributary area of the beam. So it will give you like an overall kPa or kilogram per square meter, but we will not do this because it will be already it will be picked up by the software. You want to allow for purlins as well, using LISA, Z purlins, or C, for example. Um, that will give you this much of loading. Um, it's a warehouse, so you will have services, insulation, and similar. So altogether becomes a, zero point 0.5 kPa plus the own weight of um, the beams. And live load, just referring to the Australian standard, depending on total area of the roof, you would be able to determine the kPa here. We are talking about 0.25 kPa, which is very common for roofs. So that is what we're going to do for load application. So we can apply the load frame-wise, piece by piece. Let's say that is going to be the frame, and then select it, and then go local axis, select the load case that we are talking about, and say you've got one here downwards, and apply. So you'll see the load applied onto the frame. Um, Turn off the extrusion, or the preview in here. That would be a way to do it. The loading can be applied in any direction. For example, direction 3 if you want to, which is the local axis 3 of the element. And if you are not sure about local axis, uh, turn on the local axis. 1 will be along the element, 2 will be a normal to the element vertical, or the green one, and the black one will be number 3. That applies to any frame element in the 3D. But I'm not going to apply the load using this method. You can do so many things, applying like point loads onto the frame, trapezoidal, or loads onto the nodes at the beginning and the end of the frame. There is a lot can be done using this form, but I'm not going to do it. I'm just going to undo this whole thing. I'm going to show you how you apply the load using the one-way load elements. So that's it. We've got on the calculation sheet 0.5 worth of kPa for dead loads going there. So just look at that. So we've got the purlins essentially spanning in this direction, and the roof sheeting will be sloping in that direction. So that might be a gutter location, and that would be a gutter, and that will be the summit. So that will be a ridge, valley, and so on. Click on the load element. The load in question is minus 0.5. That is dead load. So I'll just go start, and then that will show you how the load is being distributed. So it's in the direction of the red lines, but our load is going in other direction. So you just hit escape and do it again. Start. You go 1. So that is 1 span or 1 bay. And keep going. Start again. Start. And you can carry on doing this. But for now, just to demonstrate, I just click generate load. It will show you the load generated. Applied 0.5 kPa times 3 meters, which is the tributary area of each of those rafters. 0.5 times 3 becomes 1.5. I'll carry on with applying all of the loads, just noting that when we are putting another load element, it will be additive. So another one here, keep going, and then generate load. It will keep going. So I'll speed up the screen to finish applying all of the loads at the moment. Now the deadline live load have been already applied. We'll proceed to wind loading, but we will need to talk theory at the beginning. Uh, Referring to the Australian standard for wind loading, the basic wind pressure is density of the air times the square of the velocity of the wind times c fig, which is a constant that refers to the wind pressures being positive or negative. Um, if you are referring to the Australian standard, you need to apply the load in two orthogonal directions. So you need to establish distance B, D, and H. D is the depth of the structure against which the wind is applied. So it can be within on this side where to the side of the portal frame or forward blowing against the end gables. We need to work out those ratios, and from the ratios, we will establish the pressures. I'm just leaving all of those screenshots in this PDF file that will be shared in our Calc Learning Center, including the table C1 from Appendix C of Australian Standard, where you've got multi-span pitch roofs, which is our case. Essentially, you're dividing the structure into zones A, B, C, and so on. We can't dwell into the theory of this one, but in a nutshell, you're blowing the wind in this direction. So you'll have positive pressure against this wall, and the wind will go around with the vortices, and there will be a vacuum here that is causing suction or pressure in the same direction of this wind. These together will be added because CFIG is CP wind word minus leeward. This is in a negative, so they become additive together. Always on the corners, there will be a magnifier, roughly 1.5 of the wind applied. You need to apply certain scenarios, so it will be like minus 0.9 CP and minus 0.4 on those zones that you'll see on the standard. So scenario one would be this. CP is the factor multiplied by 0.6 times V squared, which is the wind loading. And it will go all upwards in this scenario. So you've got the wind apply upwards, which is going to cause uplifting. So that is another topic we can talk about. And there will be another scenario where the wind is having like reduced pressure comparing to what we've got there, and the load is downwards. And I'm assuming there will be like openings within the warehouse. So there will be some suction. So those will be added together. So scenario one and scenario two will be applied. There will be another scenario or two scenarios. Same when we apply the load from left to right, there will be from south to north. So those are the wind loads to be applied onto the structure. Back to our Calc user interface, we've learned about the load elements. So I'll be applying the same, using the same methodology. You can apply frames directly, as I mentioned before, but in this case, we will be applying the wind loading. But before that, we need to add a load case. We'll call it wind 1, or we can call it maybe wind Y and wind X. Insert wind Y and wind X, and then proceed to applying the loads. Load elements again. So we'll take this and we select wind Y, which is in this direction, and then looking at the pressure there being um, 0.97 kPa and 0.61 kPa in this scenario. 0.97 and then start. You can apply in either 3D or 2D. So let's just test one element there and then generate the load. So you see it's now throwing the load on either side of the panel. We repeat the same throughout this elevation and at the back elevation. Just mind the sign. So I recommend that you apply one load element at a time. Check the load direction. If it is in the desired direction, keep it. Otherwise, reverse this angle. Now loads have all been applied. If you want to preview the loads again, show applied loads, dead load, live load, when the next direction. I will save applying the loads onto the roof for another session, or not necessary. We just like preview results afterwards. And you've got wind in the Y direction. So all of the loads are fine. What is left now is to hit run, click on analyze, and keep watching for this. So you've got 4 load cases. So it is applying one load case at a time. So 1, 3 of 4, 4 of 4, and so on. Analysis now is completed. You can see deform shape from dead load. Click on animate to see how it looks. You can spin it around and see what is going on. Next load case is live. And then wind. You can see the wind in this direction is stressing the frames in a moment frame direction, and in one Y is taken by the brace and the top trusses. You stop the animation, and if you want to review the values, so just show values. That's all that you need to do. Zoom in. Let's say we've got the wind is blowing in this direction. You can preview UZ, and maybe for wind Y, we need to look at wind Y. You've got here 27 millimeters, which is quite high, something that we will discuss in the next session. Dead load deflections, if you want to look at UZ, you've got the deflections here as well, quite high, which is something we will be looking at in the next session as well. How we work it out, either by increasing the section or, as typically is the case, would be introducing hunch connection here and there. If you want to preview the moments, let's say you've got M33 there, you can toggle the layout as well to see it all in a full 3D. Increase the scale. You don't need to show the values at all times, and just study the or verify or make sense of the structural behavior. When the X, you see that is X direction. It's all moments coming. Like you've got here parabolic curve onto those columns, because we've got a line load, and everything goes down to triangulated bending moments in this direction. If you'd like to read the other bending, M22 here, you'll see that the central valley beam is subject to moments. We can look at those values separately. If we are looking at um, wind Y. Some moments are happening there, but what matters the most is the axial loads here. You've got the wind is blowing in this direction. So there are trusses in the roof taking the load down to the ground via vertical or like raking brace. So that is tension in yellow, compression in red. So you're blowing the wind this way. So this truss is deforming like that, and the other truss is deforming, and they are sharing the love. You've got there some 80. While you're hovering your mouse on those elements, you can just watch for what is happening there on the status bar. And this concludes the second session.